of all, thank you to all the organizers. It's very honored to be presenting this work, even though some of you probably have already seen it 2 or 3 times, like Gabriele. But basically, this is one of the latest papers that I did with Gabriela, and we submitted it recently. But it's basically a model coming from the surface quasi-geostrophic equation, SQG, but that I've seen can be connected to an ocean circulation model. So I thought this was related a bit to the planet. So let me begin just by saying a few things about the equation. So hold on, I have to minimize something here. Okay. So basically, we're looking at the critical surface quasi-geostrophic equation. I hope you can see my mouse cursor because I have nothing else to point. But so the first 3 terms are what are usually called the critical dissipative SQG. But now we're adding this dispersive forcing, which comes from this dispersive term, which comes from the Riesz transform, which I'll define in a minute, and the forcing, which is supposed to represent the wind forcing or the wind stresses. So in the SQG, we have that theta represents the surface temperature, and we can write the stream function as the inverse square root of the Laplacian, which is called lambda here. And then U, usually defined as the grad perp of the stream function, will then be the grad perp of the inverse square root of the Laplacian. And so this coupling is done by the Riesz transform, which is basically just that, the derivatives of the inverse square root. So this Laplacian is a fractional Laplacian because it's defined locally in the whole space like so. So we're looking at the equation in the whole space first. And so you can see that it has to be defined through an integral, which is non-local. You need to define the values in the whole space to know the value at a point. But in the whole space, you have the Fourier transform, and so the Riesz transforms can also be defined by Fourier transform spectrally using this formula. An important thing in this model is the fractional Laplacian term lambda of theta, which represents the Ekman pumping, which is necessary for the energy balance. And so this will be crucial to actually define what happens in the boundaries as well. This dispersive parameter, the epsilon, which we will want to see what happens to this equation when epsilon goes to 0, this is analogous to the Rossby number, which compares the nonlinearity to the Coriolis force, for instance, in the primitive or the 3D Navier-Stokes Coriolis system. But now this will actually be more related to the meridional part of the, or the meridional adduction coming from the Coriolis force. So it's a 2D sort of comparison that we're doing here. And then the last assumption that I will need to make because of the construction that I'm using is that the forcing coming from the wind stresses, the F here, is stationary. I'll try to explain why we need that. I mean, the problem without the stationary assumption is open. So in the Navier-Stokes Coriolis system, that problem for the Ekman boundary layer is solved actually. But here we couldn't manage to do it. In any case, what we want to look at now is the problem set up in an infinite strip with Dirichlet boundary conditions for the temperature. And so it's basically the strip 0 to pi in the x variable, the horizontal variable, and the vertical variable y is in the real line. So we're looking at this system with boundary conditions and initial condition theta 0, which we can assume it's in H1 with Dirichlet boundary conditions. The question of why we're choosing these boundary conditions basically has to do with the definitions that we want for the fractional Laplacian, but also because we're using a spectral approximations. And this is kind of an open problem. Matthew Novak was actually talking about this in his presentation a few weeks ago. But so we chose this approximation because it will give us the spectral approximation that we work with. And actually, this has been worked with using numerical simulations, which we'll talk about in a minute. So the important thing about this SQG system is that it's basically a high rotation, high stratification limit, which was originally found by Pierre and Bird and this group. And the thing is that it works as a basically a 2D, something between 2D and 3D dynamics. Okay, so let me just mention a few results which are related to it. So mathematically, the crucial thing about these equations is that in the critical case where you have the square root of a Laplacian here, these SQG equations, dissipative, are the correct 2D analog of the 3D Navier-Stokes. And when you don't have the dissipative term, then there will be the 2D analog of the 3D Euler system. And so just to summarize very briefly, although this is a very crucial question, a very complicated question, what happens is that the gradient of the temperature will be in 2D, play an analogous role to the vorticity in 3D. And so in 3D, one of the main things one wants to control because of the regularity questions for Navier-Stokes and Euler, one wants to control the L infinity norm of the vorticity using, for instance, the Biel-Kato-Maida criterion. And now, in analogy, we will try to control the gradient of the temperature. But this is a very complicated problem, and originally numerical simulations showed the importance of the physical importance of this model, which was that it simulated sharp fronts. And so people started guessing whether there was a possible singularity, which gave rise to the global regularity problem. And in the critical SQG, that was pretty hard. And it was originally solved by Caffarelli, Vasseur, and Kisselev, Nasarov, Wahlberg independently with very different methods. And then Konstantin and Vikol basically combined this and elaborated, showed it very explicitly how it worked. But the implicit SQG problem, for instance, is still open. And I don't think there has been a lot of progress done in that regard. But all these results were, up until maybe the last 2 or 3 years, were basically done for the whole space. More recently, the case of the bounded domain was treated by Konstantin, Ignatova, and Nguyen, with Dirichlet boundary conditions again for the temperature. But because of the boundary, and because the lambda operator will not be translation invariant due to the presence of the boundary, one loses the control of the gradient in L infinity. And so global well-postedness in a critical space is probably impossible to get. In particular, in the half plane, one can see explicitly that there is no control of the tangential velocities, which don't vanish on the boundary. So, so it makes sense then to look at what happens when you have some kind of stabilization term, like the dispersive term, and what else can you get? And this is a classical problem for the 3D Navier-Stokes Coriolis system, because then the Coriolis force can show that basically when you have large rotation, the dynamics will start going to a 2D system, and basically it will be a 2D Navier-Stokes with a damping. And this is shown in the book by Chemin, Desjardins, Gallagher, and Grenier, for instance, very explicitly. And in the case of the SQG with dispersive forcing, so for instance, Kisselev and Nasarov were the first to show this this thing converges. This thing is well posed, has global regularity with fixed dispersive parameter. And then one of the main results that we're borrowing from, in a sense, is the result by Canone, Miao, and Sue, where basically they treated the dispersive critical SQG as basically how Chemin and company do for the 3D Navier-Stokes Coriolis system in the whole space. So they do it in the whole space. So they need these dispersive estimates to show how this dispersive forcing or dispersive limit can stabilize the nonlinearity in the limit. But then these dispersive estimates were actually improved by Elguindi with Meyer, and then Wan and Chen actually showed a bit more general result for the implicit SQG. But in any case, this is what I will discuss in a minute. Okay, let me just mention very briefly, I think my slides are a lot, they're very heavy, but let me just mention what are the main things that we want to get from the physical model. So the main thing that happens in the surface of the ocean is that one can observe the western intensification of boundary currents, which is important for the ocean circulation. This is a picture that I can't remember where I actually got it from a paper by Dalibard and Saint-Raymond, who work on a very close problem to this. But again, we're trying to see how this dispersive critical SQG is the 2D analog of the 3D Navier-Stokes Coriolis system. And so we want to see how this Western intensification takes place. And what happens is that there will be a boundary layer formed. When you have the viscous effects, this is called the Monk layer. But here we're disregarding the horizontal viscous effects, right? Because we don't have a viscosity that affects the vertical direction. So what we'll have is instead a restricted part of the Monk layer, which is called the Stommel layer. And this is what really just comes from how the rotation has to do with the energy balance close to the boundary in the boundary layer. So this Stommel boundary layer explains the Western intensification via the Ekman pumping, because when you look at the equation, this is done in geophysics books, basically the Ekman pumping tells you that you have to restrict the sign of the potential vorticity, and that shows you that you can only have the Western intensification on the Western boundaries. All right, so these results, the classical results is by Desjardins and Grenier in a problem called on the homogeneous ocean circulation model, where they do this for the classical quasi-geostrophic equation, where instead of having a surface temperature, you have 2D vorticity. And then there were various generalizations. In particular, Bracco, one of the reference here, she's a geophysicist, and she worked out the first numerical simulations for the actual surface temperature model. Okay. The next geophysical application is we want to see what happens with the Rossby wave propagation, because as in the Navier-Stokes Coriolis system in 3D, and again, one of the main references here is the paper by Dalibard and Saint-Raymond, who work the beta plane model on a thin 3D strip, which is basically the Navier-Stokes Coriolis. But here they use periodic boundary conditions in the horizontal variable, so they don't deal with the Monk layer or the Stommel layer. They actually deal with that in other papers. But the main thing is that they want to get how the limiting system is derived, and how the Rossby waves are basically what drive these large-scale motions. So here I put a picture which is taken from a paper by Guillaume Lapère, who basically, he did a review paper on the SQG, which is very good and explains a lot of the stuff that I'm talking about here. But basically what you can see is that the dispersive term tells you that when this analogous Coriolis parameter is large, or rather the Rossby number is small, the rotation will dominate or will stabilize the nonlinearity, and you can see that the Rossby waves will start to form these sono jets. And in fact, the linear part of the dispersive critical SQG is analogous to the Rossby propagation equation, which Dalibard and Saint-Ramon work with. So we want to see how the critical thing here is not only do you want to have an asymptotic behavior of the energy or close to the boundary and so on, but you want to see what kind of limiting system regulates this. And this is typically a hard problem. So it's kind of like a guess, and then you have to see if you get convergence. So that was the main aim that we had in this paper, which we got basically from the paper by Canone, Miao, and Sue in the whole space. All right, so basically the outline of our argument is to do what happens for the convergence argument for the Ekman boundary layer, but now for the Stommel boundary layer for the Western boundaries. And as in the 3D case, what we want to show is that the dispersive phenomena, in other words, the stabilization, is not affected by the presence of this Stommel layer. So the main steps in this convergence argument is that basically you first have to do a boundary layer approximation. Then you have to show these dispersive and Strichartz estimates, which for general dispersive equations tell you how the space-time norms have some regularity that allow you to show the stabilization of the nonlinearity. And for instance, for the Schrodinger equation, you can get global well-posedness and so on. So once we have that, we want to do a linear approximation of the nonlinearity. So we want to show that the boundary layer or the nonlinearity induced by the boundary layer will approximate the original nonlinearity. And lastly, in this energy norm, we want to do a weak strong argument to show the convergence in energy. Okay, so with that, the main theorem that we want to use, we want to show is that if we have a global weak solution, whose existence can be done typically using the Larkin approximation, which is not unique, the global weak solution. But if you construct then boundary layer approximations to this weak solution, and then you have this spectral cutoff, which I'll define later with a parameter eta, then you can show that the linear solution starting with this boundary layer approximation, first of all, it will converge to the boundary, it will converge to global weak solution, and that the boundary layer approximations, therefore, in energy will converge to the global weak solution. So basically, we want to show that the energy is some quantity rho of epsilon eta, which goes to 0 with epsilon, the dispersive parameter, going to 0 first. Okay. But here there's a technical issue, in quotes, because we're working with a domain with boundary. We have a difference with the situation in the whole space, because in the whole space, the dispersive term doesn't contribute, doesn't modify the energy. This can be shown just by doing the Fourier transform. In other words, the energy of the dispersive term is this quantity. But here, in the case of boundaries, this will actually have an effect on the energy. And you can see that just by looking at the stationary part, you have to see that the energy of the dispersive term doesn't vanish. And so to get the approximation, you need to take that into account. But of course, if we don't have the non-contribution to the energy of the dispersive term, we will lose, at least the way we did it, we will lose the dispersive estimates and the Strichartz estimates. So we had to kind of separate what happens at the boundary from what happens in the interior of the domain to use the Strichartz and then show the stabilization. And so the way that the trick that works here is to look at the odd reflections of what happens in the original strip, 0 to pi, and then so then we're going to do a Fourier spectral representation here with signs, but then the odd reflections will also can be represented with signs, because the signs are the odd function from the minus pi to pi, are a basis for the odd functions. And so this will basically if you see what happens with the Riesz transform, because you're taking a partial derivative in x, the signs will become cosines. The spectral representation for the odd reflection will have signs. When you integrate from minus pi to pi, that gives you 0. From 0 to pi, that doesn't work. So that's why we need these odd reflections. And the main thing is that we're using this odd reflection trick just for the linear part, because that's how we construct, that's where we construct the boundary layer approximations in the original strip. That has a unique linear solution, which can be constructed using, for instance, Fourier spectral representation. And then we want to show the convergence in energy of the odd reflections, which will imply the convergence in energy in the original problem. Okay, so that's what I just said. Basically works because the linear problem preserves the odd symmetry of coming from the odd reflections. But because this will be totally confusing, I will write the odd reflections without this tilde that I used in this picture. I'm just gonna, hopefully it's clear from the context. I will basically specify which strip I will be working with. So if it's omega without the tilde, that's 0 pi cross r, and if it's omega tilde, it's minus pi cross r. Okay, so like I said, we're gonna use a spectral representation with this basis formed by signs. This is just a coefficient to normalize the basis. And then this will be an orthonormal basis for the odd functions in L2 of minus pi pi. Then we need to also look at what happens with the cosines, which will represent the Riesz transforms. And here, this will be a basis for the even functions in L2. And so once we do that, we can define a so-called Fourier transform for the strip. In other words, just a Fourier spectral representation. Obviously, it doesn't have all the properties of the Fourier transform in the whole space, but it's this is basically the trick that, or the structure that Chemin and company do for the 3D Navier-Stokes Coriolis for the Ekman boundary layer problem. And so this is a continuous isometry in L2. We can then define spectral projectors or spectral cutoffs by basically doing the spectral representation, doing a cutoff in the Fourier space, in the Fourier side, and then taking the inverse Fourier spectral representation. So here we're working with cutoffs on balls where the frequencies are bounded by some n. Okay. So with that, using the spectral theorem, one can define a fractional Laplacian, as one typically does in the whole space, just by, so that the symbol of the lambda to the alpha will just be c to the alpha. Then we have the Plancherel theorem. As usual, this can all be done using the sign basis, or the spectral representation. We have the Plancherel theorem. Then for the Riesz transform, we can define the lambda inverse as 1 over c, and then take the partial in x that takes out or gives us a factor of k here, and it transforms the sign basis to the cosine basis ck. So one important thing is that the R1 Riesz transform will not vanish. By the way, the R1 Riesz transform is just the vertical component of the velocity, because of the coupling, U2 is R1 theta. So this will not vanish on the boundary of the strip omega or the extended strip omega tilde. But like I said before, because of the orthogonality of sines and cosines in minus pi pi, we have the important property that in the extended problem for the odd reflections, the dispersive energy, or this dispersive term, will not have energy. And also, this is just an easy exercise using the spectral representation. You can show that the Riesz transforms are bounded in L2, which is one of the main properties of the Riesz transform, which works in general, in fact, in many situations. Okay, so the main thing we want to do now is construct the boundary layer in the original strip. this is done typically by using, you look at, so because of the forcing is stationary, the boundary layer approximation will also be stationary, as I'll show in a minute. And if you look at the stationary part of the DCSQG, that can be written as this parabolic problem for, or sort of elliptic problem for the stream function psi. This is called a convection diffusion problem. But you can see that when epsilon goes to 0, this becomes a singular, and so we will have a boundary layer. To construct the boundary layer, we use the typical ansatz with interior terms and boundary layer terms or boundary layer correctors, which correct the boundary layer the boundary conditions for the approximation at each order epsilon. And so if you just plug in this ansatz into the equation, to the stationary part, what you will get at leading order is this Sverdrup relation, which is classical, and tells you how to construct the first interior term from the forcing, just by integrating like this. Then, sorry, here I have a typo. This should not be +1. This should just be x. I have a typo because I wrote it in a different way before. But then the boundary layer corrector is just what, because this will not vanish on the boundary in principle. It will have to vanish on the eastern boundary, but on the western boundary, we need to correct it. So when x equals 0, we need to correct it with this boundary layer corrector. And then by recursion, this construction works like this. And one of the main things that we have to see here, again, this is a typo. This should be this -1 should be 0, and this 1 should be pi. But the main thing is that if you look at this construction, also we need to look when we apply the lambda, because lambda of psi is theta, we need to apply lambda to the sum of the interior and the boundary layer corrector, because otherwise we cannot apply it separately because we need the Dirichlet boundary conditions. But you can see that from this construction, because this all of this starts from the forcing, which is independent of time, it's stationary, the partial in time can be commuted with the lambda here, and so we'll also get that at each order, the boundary layer terms are stationary. Okay, so this is in the original strip. The rest of the stuff will be basically in the extended strip. Okay, this is a typical linear error estimate. Basically, we can define by just applying lambda to the psi boundary layer expansion. We can define the boundary layer approximation for the theta. And then we have a linear error estimate in L infinity in time, L2, and L2 in time, H0 1/2. So in the energy norm of the boundary layer approximations to the solution of the linear problem.
Leonardo, you have
yes.
5 minutes, sorry.
5 minutes?
Yeah.
Okay.
If you, yeah, maybe just take,
okay,
take the whole 5 minutes, let's say.
Yeah, sorry. I guess I went too much into the physics perhaps, but anyway, this linear stuff for the boundary layer is classical. Although here, again, the odd reflections were important for us to work out the Strichartz estimates and so on. But okay, obviously I planned in a very different time scale what I would have to show. But we have these error estimates. Then one thing we have to assume from the forcing is that it has an O of epsilon decay in the L2 norm. This actually is analogous to a condition for the forcing in the classical quasi-geostrophic system. But here we also need it for the Strichartz estimates that we're going to use. They will have the L2 norm of the forcing. And because that comes with 1 over epsilon from the dispersive forcing, we need this decay in order for that to be bounded. In any case, this condition gives us that the boundary layer approximations in L2 are bounded in epsilon. So that won't give us a problem. Then we have the linear convergence in energy is basically, it's basically classical. You just have to integrate in time, multiply, integrate in time, and you get this approximations. So the convergence in the linear part is easy. Now we want to show the Strichartz estimates, and let me just say very rapidly what happens. So Strichartz estimates are these kind of mixed space-time norm decay estimates, which tell you that with the dispersive parameter going to 0, you will also control these the mixed norms, right? But one thing that is a problem here is that in the original SQG, the Riesz transform, because it has a partial in X, will have to be spectrally represented with cosines. But then that doesn't vanish on the boundary. And that gives us a problem because we want to use the spectral representations for the Strichartz estimates. And so the trick that we used here is to define an auxiliary Riesz transform, which is just the same as this, but with the sign basis, the decay basis. And then we look at the auxiliary linear problem. Then, so the linear problem can be solved using the Duhamel formula because you can apply the Fourier spectral representation. You have a semigroup, and basically you want to get a decay for this semigroup G epsilon, capital G epsilon. So we'll show the Strichartz estimate using the spectral theory for the auxiliary linear problem, which is for theta star. And this, because we're only changing signs with cosines, will give us a control in the L2 norm in X, and we can then extend the Strichartz estimates for the original problem. So we'll just skip most of this. That's one of the main parts. But so this is the technical part of the paper. But to do the Strichartz estimates, you need to show how the kernel of the semigroup, which is this, has a dispersive time decay. That's classical, but I won't be able to get into that. So let me just skip the Strichartz part, which gives us the decay of the mixed norms. And all we want to do now is control the nonlinearity induced by the boundary layer. And this can be done using the spectral representations that we had before with cutoffs that we need, spectral cutoffs. And then this is also one thing that I just want to say here is, okay, so if you look at this part of the other part of the nonlinearity, how the boundary layer affects the nonlinearity, delta will be the difference of the Wick solution with the boundary layer approximation. But what happens here is that you will have a gradient in L infinity to control, which was one of the basic things. And so using the Strichartz estimates, you can pass to the L infinity Y, L2X norm. And that will give you the decay in epsilon to show that this is a control term. So we can deal with the nonlinearity. We'll get to stabilization. Okay, so that's just classical. And lastly, for the convergence in energy, I just wanted to say, so basically here we extended the energy decomposition, which is done, for instance, in the 3D Navier-Stokes-Coriolis problem. And the first line is just the linear part of the problem, so that's going to be controlled. For the other parts, we just have to use the nonlinear estimates that we had before. And this one, for instance, is just controlled in L2 by the first nonlinear estimate. And for this one, basically, you have to decompose using a Young inequality, and then, then just use the Strichartz estimates to control, for instance, the gradient in L infinity Y, L2X. Okay, so that was basically my last slide. I calculated these awfully in terms of time, but in the end, what one gets is the convergence in energy, and finally, that the linear part of the DC SQG will be the limiting system. So the Rossby waves are, at least in this model, what dominates the large scales for the surface temperature. Okay, thank you very much. Grazie mille.